In this lesson, we're going to look at proofs involving summations. This is a specific example of the types of induction proofs that come about when you're trying to prove summations. Let's jump right into an example. Again, you need to know how to use induction to do these, so if you haven't looked at this, please see my video on induction proofs prior to looking at this one. Let's start off with our base case. Let n equal 1. That's our first value in this summation. Then what we'll do is plug in 1 into the left side and into the right side and show that they're equal. Then the sum I equals 1 to 1 of I is equal to, well, this looks a little bit strange, but the fact that the numbers match with the bottom and the top simply means I'm just going to plug in 1 for I, and there you have it. And 1 times 1 plus 1 over 2, well, if you calculate that out, I think it's pretty easy to see that number is also 1. Now let's go to our inductive case. Again, for induction, we start out by doing the base case, but then for the inductive case, we assume that the statement is true for some k, and show that the statement is true for k plus 1. Assume that the summation, I equals 1 to k, of I, is equal to k times k plus 1 over 2 for some k greater than or equal to 1. And then let's write down what we're trying to show. We want to show that the summation for I equals 1 to k plus 1 now, of I, is equal to, this becomes k plus 1 over here. But then k plus 1, if I put in a k plus 1 on the k, I actually end up with k plus 2. Now for these summation proofs, the ideas from the last lesson in induction still hold. You want to start with the left side and show that it eventually looks like the right side. Sometimes you might want to simplify this statement in order to more easily show it, but sometimes you can leave it be and use factoring a bit in a clever manner to make this problem easy. That's what we'll do for this one. Then the summation for I equals 1 to k plus 1 of I is equal to. For these summation proofs, you're always going to have the same type of thing happening. You're going to want to split your sum into pieces so that you get a piece for the inductive hypothesis, and then you get one or more pieces that are left over that you'll have to work around to clean things up. Let's split our sum carefully. I'm going to split it to the sum from 1 to k of I, but then I have a k plus 1 here. So what I'm going to do is plug k plus 1 in as if it's some new term that I'm taking out of the sum. So I is getting k plus 1 plugged in. Now what I'll do is use my inductive hypothesis. I know that this sum here, which by the way is the same as this sum, is equal to k times k plus 1 over 2. That is my inductive hypothesis. But I also still have this plus k plus 1 here. And now I need to somehow show that this looks like k plus 1 times k plus 2 over 2. The clever way to do this is actually factor a k plus 1 out of the full expression. I'm left with k over 2, and then this term just becomes a 1. Now k over 2 plus 1 I could put in a common denominator, and I get k plus 1 still sitting in the front. But then k over 2 can be plus 2 over 2, and I get k plus 2 over 2. Now look at the similarities. That's just a multiplicative difference in writing it. Well, let's write it that way. This is k plus 1 times k plus 2 over 2. Now we're finished. We showed that the equality holds, so we just need to write our summary sentence. Thus, by induction, the summation for I equals 1 to n of I is equal to n times n plus 1 over 2 for all n greater than or equal to 1. And that is the end of our proof. For our next example, we'll do this with I squared rather than I. Let's jump right into the proof. For our base case, we will let n equal 1, and then we'll plug 1 in for n in both sides of the summation. Then the summation for I equals 1 to 1 of I squared, again that just means plug in 1 for I, and I get 1 on the left. And on the right, I plug in 1 for n, and this turns out to also be 1. Now let's do our inductive case. Assume the sum for I equals 1 to k of I squared is equal to k times k plus 1 times 2k plus 1 over 6 for some k greater than or equal to 1. Assume it holds for some k, and then we're going to show it holds for k plus 1. I'm showing that the sum for I equals 1 to k plus 1 of I squared is equal to k plus 1, which is what this k becomes, k plus 2, which is what this k plus 1 becomes. But then you need to be careful right here. Where I had 2k plus 1 before, k is what's becoming k plus 1. So I put that in parentheses. Let me simplify that one more step. That's actually equal to k plus 1 times k plus 2 times 2k plus 3 over 6. Now this is what I'm going to try to show. Then the summation, I equals 1 to k plus 1 of I squared, is equal to, and just like in the last proof, we're actually going to split this. We're going to go from 1 to k of I squared, so that we can use this inductive hypothesis here, but then we've got a leftover k plus 1 term. So for the k plus 1 term, I need to plug it in for I, and I end up with a k plus 1 squared. Now let's use this inductive hypothesis. This part, I have a statement for. That's k times k plus 1 times 2k plus 1 over 6. So here it is. And then I still have a k plus 1 squared. Now just like in the last proof when I did some clever factoring, I'm going to do that again. But this time I'm going to be even more smart about it. I'm looking for a k plus 1 times k plus 2 times 2k plus 3 over 6. I see a k plus 1 in both terms. There's also an over 6 in the first term. So I'm going to factor out k plus 1 over 6. Now that might look a little bit strange, but here's what's left after I do this. I get k times 2k plus 1. And then for this second term, when I factor out one of the k plus 1s, another one remains. But when I factor out the over 6, the way to remedy that the over 6 was taken out is to multiply by 6. And then again, I've still got a k plus 1. You might find it meaningful to try distributing this back and see how the 6's cancel here and here to give us back what we had. Now the whole point of doing this is so that the algebra is a little bit easier, although I will give you that the way that I did it was a little bit tricky. Now let's multiply everything out in here. I get 2k squared plus k plus 6k plus 6. And that becomes 2k squared plus 7k plus 6. Now we're almost there. We're trying to make the expression look like this, but right now I have it looking like this. Fortunately, if you think about factoring this expression, it actually comes out to be the very k plus 2 times 2k plus 3 that you wanted. Now you don't necessarily have to factor it. You could just come over here and multiply these two together and say, look, that's the same as this. In other words, we can use the factoring to rewrite. Again, the over 6 can be applied to the whole thing, and here's what we get. The answer that I was looking for. Now let's write our summary sentence. Thus, by induction, the summation I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 over 6 for all n greater than or equal to 1. And that is the end of our proof. These summations all seem to have the same sort of pattern. For your base case, you'll plug it in on the left and the right. And for the inductive case, you're always going to have this k plus 1 style term, or perhaps a 2k plus 2 if it had a little bit more than just k on top. But whatever the case, you're always going to be able to break your sum up into one piece corresponding to the inductive hypothesis, and a little bit more corresponding to what's left.